Unit 7 deals with similarity, and we're going to learn about similar polygons a little bit here and there, but we're going to try to define it in terms of the transformations that we used in Unit 3. These are not going to be rigid transformations, rigid motions. These transformations are going to be dilations. And so we'll focus on that, applying some of the skills from Unit 3 here in our next couple lessons. So in order to do that well, we want to make sure that as we approach dilations, that we have some good materials. We're going to need a ruler, a measuring stick of some kind that we can actually measure, not just a straight edge, but an actual ruler so we can do some measurements. And you're going to want quad rule paper. You're going to want graph paper. It will help you do the work here very well. So on your notes, pause the video, go get your graph paper, and then take these notes. Let's start to understand what a dilation is, all right? A dilation basically is where you take a figure and you either reduce it, you shrink it down, or you enlarge it, you make it big. And it is going to be performed in two different ways. We're either going to approach it using algebra and measurement, or we're going to do geometry where we're using parallelism as an approach. We're still doing some measurement, we're still maybe doing some multiplication or division, but we're then applying parallelism throughout. Because one of the things that you're going to notice is that kind of like when you would do perspective drawings in your art class, where you try to do a three-dimensional render and you'd say, oh, there's the horizon, and so there's kind of a focal point in the background, and you kind of draw your the town square in perspective. So P here is our center of dilation. This is the part. It might be outside of the figure, it might be inside of the figure, it can be to the right, to the left, it doesn't matter where it is. But what we want to do is be able to connect that center of dilation to each of the vertices in our pre-image. So again, the vocabulary there, pre-image is the figure that's drawn here in black. The image that is new, that you drew, is going to be in this red or this orange. So we want to connect these with rays, and those rays extend infinitely, but depending on the situation, you will either stop drawing the ray at the vertices or you will continue on. You would continue on if you're doing an enlargement where you're making the picture bigger. You can stop at the vertices if you're shrinking it down, if you are doing a reduction and making the picture, the image, smaller than the original. All right, so P is the center of dilation. Triangle ABC, A prime, B prime, C prime is the image of triangle ABC. There's that vocabulary. Corresponding angles. These corresponding angles are congruent to one another. So the angle at B prime is congruent to the angle at B. They have the same measure. When you do this enlarging or the shrinking, the angles maintain their measure, all right? But the sides are going to be proportional in length. They're either going to shrink the same way, this one is smaller than this, in the same way that this side of the triangle is smaller than that. It's the same scale factor by which we shrink or enlarge the dimensions of the shape. So this is what a dilation is, all right? Just think about like when your pupils dilate, when you get closer and then your pupils shrink, all right? Or they get bigger if it gets darker. That kind of dilation is what we are focusing on, all right? Now, there are two methods to perform a dilation. One is probably favored. The first method here is what we're going to probably do. That, of course, is going to be up to you. Whichever approach you want to take, you have that freedom. All right, but with great freedom comes great responsibility. You guys know that. And so whatever method you choose to do, you can be flexible. It's not like you have to pick one and stick with it. But I think that you're going to find method one a whole lot easier. It's easier to repeat. It's easier to have a concrete, firm result. And so that's one thing that I want to encourage you with. First method, if we want to take this triangle ABC and we want to dilate it around point P, center of dilation, by a factor of 1/2, by a scale factor of 1/2, we're doing a reduction there, we're shrinking its size. The way that we would do that is we would, again, have our rays drawn, PB, PA, and PC, and we're going to measure a spot that is halfway between the vertices, each of the vertices, and that point of dilation. So A prime is halfway between P and A. B prime is halfway between P and B. C prime is halfway between P and C. And so we would measure this distance and cut it in half. We would measure this distance and cut it in half. We would measure this distance and cut it in half. And once you plot those vertices of your image, you connect those vertices using your ruler. All right? It does require that you measure, and it does require then that you connect those vertices using your straight edge. So this new triangle, this image, A prime, B prime, C prime, is a copy. It's a version of this original, but it's not a copy in that it's congruent. It's a copy in that it maintains the angle measures. But it's a scaled version, a scaled down, in this case, a scaled down version is a smaller version of that original. The other method that we would approach would be using more of a geometric approach, okay? Where here in this version, the point of dilation or the center of dilation is inside the figure. The location doesn't matter. Again, you would follow the same steps if it's inside or outside. All right, but here, point Q is our point of dilation, and our image is WXYZ, this quadrilateral. Or our pre-image is WXYZ, this quadrilateral. We're still going to draw those rays through point W, through point X, through point Y, and through point Z. We are dilating this by a factor of 2, meaning that our new picture is going to be bigger than, it's going to be outside of the original, all right? And it's going to be larger than, each of the sides is going to be twice as long. This side is twice as long, all right, when we have the new image. The way that you can do this more of a geometric approach still includes a little bit of measurement. The way that they instruct you to do this, and you can read all the steps there, that's what I'm doing basically, is we take that length and say, all right, well this was 7 or 6.5 centimeters. If it was 6.5 centimeters, then now I'm going to plot this one that is 13 centimeters away. Point W prime is going to be twice as far away from point Q as the original pre-image, W. But then what you do is you draw a segment parallel to the given segment through or to the next ray, all right? To the next ray, all right? These are parallel, these are parallel, these are parallel, those are parallel. That requires, that's a little bit tough to do kind of on like a blank sheet of paper, but if you are using a coordinate plane, if you're using quad ruled paper, which you should be doing right now, then it is much easier to find where that, or to draw well those segments parallel to the original, all right, because you're going to use the same slope, all right, so you can count that out, and it works itself out quite well. All right, moving on. So what I'm going to do is I'm going to do this 2 different ways. There's method 1 and then there's method 2. And I'm going to do the same thing. What I would recommend that you do is that you draw a version of this on graph paper. If you draw a version of it on graph paper, it'll be much easier for you to copy it correctly. All right, so do your best work, or I guess just find your best way. So we're going to dilate this triangle JKL by a factor of 2. The first thing that I'm going to do is draw in my rays. When I draw in those rays, I want to make sure that I go from the center of dilation R through each of the vertices. These should be kind of like dashed or dotted segments. You can use different colors here to sort of keep your stuff all straight. And when I draw in those rays, it gives me this freedom to measure from RK and double it. To measure from R to J, and then double it. To measure from R to L, and then double it. So I'm going to use my ruler here, and you're going to use yours. My numbers are going to be different than your numbers because our pictures aren't exactly the same, but you have the capability to measure what's on your own paper. And so I measured this, and I find that this is about 5.5 centimeters. So I'm going to have to count out. I'm counting from the center of the points. So 5.5 doubled is 11. So I'm going to go all the way down to here-ish. All right, that should be on that ray. Over here, this distance is roughly 11, let's just call it 11.25, or we can just say it's 11, kind of depending on your situation. So I'm going to double that to make it go 22. I'm going to go 22.5 though, because that would be a little bit larger. That would incorporate that quarter that I think I saw. All right, and then here, this measures about, let's just call it 13.5. So doubling 13.5 would be 27, I can count. 10, 20, and 7. So I'll put that over there, again, on this line. All right, that looks pretty good, right? And so each of those points that I plotted, and I don't know how well you can see those, but I'm going to put those dots here. These are now J prime, K prime, and L prime. Now, on this part, I'm going to connect those vertices. Again, to the center of the point. The center of the point should be on your ray. And when I draw this new figure, J prime, K prime, L prime, each of the sides should be parallel to the original, which is the method we're going to use in method 2, and each of the sides should be twice as long as the originals. All right? And so since we did a dilation that was an enlargement, our sides are bigger. In the previous exercise, they were smaller. All right? And you're going to do one that's smaller in just a second. Over here, if I'm going to use method 2, we're going to do the same thing. And you can decide which method you like better, but I'd love for you to practice both of these. And so follow along as best you can on this, but I'm going to do the same thing where I draw in these special rays that go from our center of dilation through our vertices. And hopefully I'll do a good job of that. These should be probably dashed rays. It doesn't really matter, but just it helps keep you focused, especially if you're using one color. It can kind of make your life a little bit easier. We do get to measure one of our point placements, all right? One of our points, our image points placement. So given the pre-image JKL, I'm going to start with K just because, I don't know, it's easier for me. And I measure that is about 5.5 centimeters. So I'm going to pick a point that is double that, which is 11 centimeters off. Now, I'm not going to measure the others. Instead, I'm going to use parallelism. And like I said, this is easier to do if you have it on quad rule paper, on graph paper. It's going to turn out better if you're doing it on graph paper. I'm not modeling that very well, I apologize. But what I'm going to do is I'm going to draw a segment here that is parallel to segment JK. And I feel like I'm pretty good at that. So I'm going to draw that segment right there from K prime to what is now going to be J prime. And then from here, I'm going to draw a segment here that is going to be parallel to JL, but passes through point J prime and touches that ray where L prime is going to be. And then the same thing's going to happen. I should be able to connect those 2 points, and that segment should be parallel to our original segment KL. Those triangles, if I did a good job, which maybe I did, maybe I didn't, those triangles, JKL, J prime, K prime, L prime, and J prime, K prime, L prime, should be congruent triangles, all right? If I've started with the same triangle and I did both methods, I should have the same result, all right? So that should give you that freedom. That should give you that flexibility to choose a method that works for you. You may be better at saying, I'm going to measure, I'm going to measure, I'm going to measure, and go from there. Or perhaps you would like to use parallelism. My only warning about parallelism is that you have to understand parallelism in the coordinate plane, that Algebra 1, Unit 6, where you know that parallel lines have the same slope. So use that if you're going to use that approach. I know that's more of a geometric approach, but it requires an algebraic understanding. I would like for you to do these, all right? I'm not going to sit here for too long. I'll give you a chance to copy these figures down. Your dilation factor is going to be 1/3, which means that this is not an enlargement. It's not an enlargement. You are reducing the size here. So you're going to make a figure that's smaller. Our point of dilation is outside of the figure. So when you draw in your rays, your figure is going to be smaller. It's going to be moved this direction. All right? Do your best work there using method 1, where we measure out a distance that's 1/3 of the way between each of these, or pick one of those and then draw parallel segments from there to your rays. All right. Pause it because you're going to need more time on that. All right, here's a basic summary here of this concept. I'll give you time to kind of get that down. If you need explanation on these, then I'm happy to explain it further. But we are going to use K to represent our scale factor. And that might be slightly different than how it's listed in the book. It's listed originally as N, and then they call it K. And so I'm going to be consistent here that the scale factor is K. It's some constant that we are multiplying the lengths of our segments by. All right? And this sort of summarizes what you're seeing in that picture. C and C prime map to the same place in this case, because the center is located in that same place. And so just kind of keep that in mind. So dilation D sub K comma C, this is your scale factor, and C is your center of dilation. And here you can see that we took XR, and it looks like we enlarged it. We made it bigger because our K value is bigger than 1. And here, it doesn't tell us what that is, but we can kind of think through that relationship. Once you have that down, move on to the next slide. All right, now for this part, oops, this is supposed to come up separate, but I'm going to do this one, and then you're going to do that one. I was hoping that these would pop up separately, but they didn't. So here, I'm going to show you this. And we can understand that we've got these segments drawn, and that's fine and dandy. I'm not going to actually worry about those rays, but understand that they are there, and it might help you visualize things better if you'd like to draw them. Basically, here's what I want to do. And you're going to do this with this example. I'm going to do this with this one. Please have both of them down in your notes. But basically, when we're drawing our scale factor, we are going to compare the lengths of corresponding sides. All right? And what we should note is that segment A prime B prime's length divided by segment AB's length is going to be the same ratio, the same scale factor as B prime C prime's length divided by BC's length. All right? So it doesn't matter which one we use, but here I get to count that because we're on a coordinate plane or on quad rule paper, so I can actually count that out. And I should be able to see that this is 1, 2, 3, 4, 5, 6 units, whereas this is only 2. And that should be the same ratio, which simplifies to be 3, for this length, 1, 2, 3, 4, 5, 6, 7, 8, 9 boxes, over 1, 2, 3 boxes. All right? This tells us what our scale factor is. All right? This lets us know that our sides are proportional in length. Furthermore, we should be able to tell that our angles are congruent. All right? We can see here that this is, obviously this is rectangle, and so our angle measures stay the same. Our angle measures are not affected by the scale factor. All right? So we're not going to take, oh, this was 90, and now it's going to be, 3 times as big. All right? No, we don't all of a sudden have a 270-degree angle here. It maintains the same angle measure. All right? The sides are what are proportional. Do the same analysis, answer these 2 questions using this example. All right? And then move on. All right, example 3. I just kind of modeled how to find the scale factor. Given the image and the pre-image, we are going to calculate that value. So here we have the pre-image, J, K, L, M, and then we have the image, J prime, K prime, L prime, M prime. And what we're going to do is compare our new length for side LK to our original length for side LK. So this is L prime K prime, this is LK, and we then simplify that ratio. All right? When we do that, this tells us our scale factor. Our scale factor is 3/2, or 1.5, which means that if I were to measure this and then multiply it by 1.5, I would get that. Same thing here, multiply by 1.5, you get this, etc., etc., etc. It should not matter if our scale factor is a fraction, if it is a fraction bigger than 1, if it's a fraction less than 1, or if it's a whole number. All right? You're never going to have negative numbers. You're not going to have a scale factor that's 0, right? That would just obliterate the item. You may have a scale factor of 1. If you have a scale factor of 1, that means you're talking about congruent figures, all right? Because the sides are proportional in a 1-to-1 ratio. All right? Think on that a little bit. I know that sometimes the language of fractions gets a little bit complicated. All right. So we're able to find the scale factor. Can you try this? See if you can ascertain, is this an enlargement or is it a reduction? What is that scale factor? Can we tell how the lengths either got larger or smaller comparing your image to your pre-image? Do that one. All right, and then this is the last one I'm going to do. What are the vertices of D sub 3 of triangle ABC? Let me explain what this means. Our scale factor is 3. Let me write that a little bit better. All right? But in the previous notation, we had K comma C. So why do I not have a comma there? Why do I not have a C value? In the coordinate plane, if it's not given, the center of dilation, wow, the center of dilation is the origin. All right, and that's going to be my focus here. I don't want to deal with centers of dilation that are not on the origin. This is going to make our lives just a little bit easier when we're working them backwards. Obviously, if I were to plot a center of dilation out here and you needed to make things grow bigger or shrink smaller, we could make that happen. But for these instances, I just want to use this approach right here to make your lives a little bit easier. So what we can do and how we would approach this is instead of saying like, well, let's compute the length here by using the distance formula and then let's find a length that's 3 times longer, and then try to position those segments in such a way that they all intersect on the given rays from the origin there, and because that can get a little bit complicated. So instead what I want to do is take the x comma y's and triple them. All right? If my scale factor is 3, I'm going to multiply this times 3, 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 this times 3. If I multiply them all by 3, then now I have an x comma y from the origin that is 3 times farther away. All right? And so that's what makes this go a little bit easier if we have our center of dilation on the origin. All right? So when we do that multiplication, you can see the scale factor 3 is in red. All right? So follow along there. 3 times this 2, 3 times this -1, 3 times that 3, 3 times that -1, 3 times that 2, 3 times that 0. And that gives us a new set of points. If we have that new set of points, then we can plot those dots accordingly. All right? I drew my lines pretty well. We can plot those points accordingly, and that gives us our new image that is having sides 3 times as long as the originals, all right, parallel to the originals, and centered around our origin. All right? What I would like for you to try is, what if we took this and we fixed the values by a ratio, not of 3 this time, but a ratio of, or a scale factor of 1/4. All right? And so what we're going to do here is we are going to multiply each of these by 1/4. I said I was going to have you do it, but I'll go ahead and do it. Let's go ahead and think through that together. This will be in real time. So I'm going to take 1/4 of 8, comma 1/4 of 4, and that's going to give me 2, comma 1 for our p prime. 2, comma 1 is where p prime is. Oops, I should do that in red, shouldn't I? 1/4 of this, comma 1/4 of that. That's going to give us 1/4 of 12. Sorry for my handwriting. 1/4 of 12 is 3. 1/4 of -4 is -1. And so that gives us 3, comma -1 for q prime. I would like for you to find r prime, and then I would like for you to connect the dots. When you connect the vertices, you will have your reduced figure. It's reduced because our scale factor is less than 1, between 0 and 1. The previous example, it was an enlargement because our scale factor was bigger than 1. All right? So at the end of, what the heck, I'll just do it for you. Who cares? No, you're going to do it. And then we'll check it. We'll see what your triangle looks like on your graph paper. All right, so hopefully at the end of this conversation, you feel comfortable with what dilations are, that you can identify what's happening with these dilations, and that you can understand how to execute those dilations, or if you see a dilation that's happened, you can think it in reverse to identify what's the scale factor, etc. We'll do more with this in the coordinate plane for lesson 2.